Morning, students. Good morning. Are you able to see the slide displayed there?
Yes, ma'am.
Okay, thank you. And I hope I'm clearly audible. Fine. Hope all are doing good. 46 of you are present here now. And the time is exactly 9. I don't know why others have problem logging in. Okay, we'll just wait for a few more seconds and then start. I hope you have gone through the Google Classroom where I have shared all the instructions about the assignment. The link of the website is shared there where you have to conduct your virtual lab experiment. Fine. Okay, we'll start the day. So, as usual, as daily I mention, as I'll be looking at the slides, please, if you want to say something, stop me in between. You have to unmute yourself and speak up. Okay. All right. So, in this class, by the end of this class, you will be able to describe the ideal diode characteristics and also demonstrate the equivalent circuit of a diode. All right. So, from the previous discussions what we have and the knowledge and information what we have got now, we have understood that whenever external voltage is applied across the terminals of the diode, then if the externally applied voltage is more than, say, the cut-in voltage, or we can also say it as a threshold voltage, then the diode conducts. So when the diode conducts, we mean to say that there is a full flow of current flowing through the device. All right. So in a similar way, we also saw that whenever the diode is reverse biased, that is when a reverse voltage is applied, we saw there that it does not conduct. Okay. So there is no current flowing through typically, right? So say if we are using this diode in our electrical or electronic circuits, so say if we want to find the current or say voltage that is across the diode, it's not that we can always go to Shockley equation and apply the exponential formula there to find the values, right? So I hope you remember the Shockley equation, what we discussed yesterday, which gives the exponential relationship between current and voltage, right? So every time whenever a diode is used in a circuit, we need not apply this exponential formula to find the values of voltage or current. Okay, we can always approximate the characteristics of diode by replacing the diode in the circuit with its equivalent circuit. So what I'm mean to say here is an equivalent circuit is nothing but a combination of elements that best represents the actual terminal characteristics of the diode, okay, or of the device. In simple language, it simply means that diode in a circuit can be replaced by other elements without severely affecting the behavior of the circuit. I hope you're with me. Okay. So the diode can be modeled in 3 different ways depending on the accuracy that we require. Okay. Based on that, we have 3 different equivalent models. One is the ideal diode model. Second is simplified or approximate model. And third is the piecewise linear model. All right. So we will be discussing all these different models, which are nothing but the equivalent models, where whenever we want to analyze any circuit where we have diodes in them, okay, circuits with the diodes, if you want to analyze them, then we will go for the equivalent circuits using either ideal diode method or approximate method or piecewise linear method. So we will discuss all these today. All right. So typically we know that where diode is forward biased, right? The figure indicates when a voltage drop is across drop across the diode is 0 for any value of diode current, right? Whenever the diode is conducting, that means voltage drop across it will be 0. That means from the figure here, you can see if a forward voltage is applied to the diode, it simply acts as a short circuit. Okay, you can imagine it as a short circuit or say closed switch as indicated here. Okay, so if the voltage applied to the diode is reverse bias, I hope you remember the condition there, then the diode will not conduct. So we can take it as say open switch, right? So you can also take an analogy of the water pipe with the hinge there. Okay, so the water will be allowed in only one direction, as you can observe here. In the reverse direction, water doesn't flow. So similarly, it is a simple analogy for the diode. The current in the diode will be always flowing in one direction. So looking at the characteristic there, the ideal diode does not allow any current to flow in reverse bias condition, isn't it? We are now in a stage that we understand that whenever a forward voltage is applied, full current will be flowing through, and whenever the diode is reverse bias, there is no current flowing through. Okay, so the current flowing through the diode is 0 for any value of reverse bias voltage. So taking this into consideration, the ideal diode can be modeled as open switch or closed switch, as indicated here in the figure. I hope you are able to see the screen. Can anyone acknowledge?
Yes,
ma'am.
Okay, fine. So ideal diode allows a flow of forward current for any value of forward bias voltage, right? So hence the ideal diode can be modeled as a closed switch under forward bias condition, as you can see here in the figure. So in other words, in an ideal diode, if the voltage across it tends to exceed 0, say imagine any voltage that is applied, if it exceeds 0, then current flows. We say that there is full current flowing through it. It is, isn't it? So if the voltage is greater than 0, any value greater than 0 here in the x-axis, as you can observe, there is full current flowing through. So that we can take it as a closed switch condition. All right. Similarly, if a diode allows 0 current to flow in the reverse bias condition, what we have discussed till now, there is no current at all in this reverse bias condition. Okay, then the diode can be considered as an open switch, as you can observe here. So imagine if the applied voltage VD, I'll take it as VD here. If VD is less than VD on is the, say, the voltage that is required for the diode to conduct, and there is full current. Okay, if VD is less than VD on, right, then we say the applied voltage is reverse voltage. Okay, that means there is no current flowing through. So this would be the typical characteristics of an ideal diode, as you can observe there, right? So if the voltage across anode and cathode is greater than 0, right? If the voltage across anode and cathode, if it is greater than 0, what about the resistance? We know that there is full current flowing through, right? So when the current is maximum, resistance will be less. So in ideal condition, can we take it as 0? Resistance will be 0, right? In ideal condition. I hope you are with me. If the voltage applied across anode and cathode, if it is greater than 0, then the resistance of an ideal diode is 0 there, because current is maximum, current is infinite. I hope you're following my mouse there, right? In a similar way, if the voltage is less than 0, okay, then there is no current flowing through. That is what we have seen, discussed now. That means what? Resistance will be infinite. Okay, so typically, as you can observe there, if for ideal diode condition, the ideal diode would have 0 forward resistance. Okay, 0 forward resistance. You can observe the figure there, A and B as well. Okay, 0 forward resistance, 0 forward voltage drop. That means whenever there is maximum current, the drop across the diode would be 0. So ideally, when we say voltage is more than 0, that is applied voltage is more than 0, then the voltage drop across the diode would be 0, and current flowing through it would be maximum. Okay, so which would give us, in an ideal condition, 0 forward resistance. There will be 0 forward resistance, 0 forward voltage drop, all right, and infinitely high resistance, high reverse resistance, RF will be high, maximum. So typically, as you can observe here, the slope of the forward characteristics is infinite, isn't it? That represents this vertical line. All right. So since the reverse resistance is infinite, you can observe the slope is 0 there, and the line is horizontal, as you can observe. Okay. So typically you can take this as the current voltage characteristics of an ideal diode. I hope you are with me. Are you with me? Okay. Observe this. Yeah. Observe this circuit where we have a DC voltage VA diode, which is connected in series with the resistor. All right. So say if VA is, say, sufficiently more, say VA is greater than 0, then the diode will be forward biased. So when the diode is forward biased, we have discussed till now that whenever the diode is conducting, it acts as a closed switch. So closed switch means it will be simply shorted. Okay. So you can imagine the circuit where the current flowing through is simply via the resistor. Okay. So diode, when it is conducting, you can imagine it as a closed switch condition, or you can also take it as a short circuit here. All right. So when it is conducting, full current will be flowing through the diode. All right. So the circuit can be taken as, equivalent circuit can be taken as the resistance here, as shown here. All right. Whereas if the applied voltage is less, say reverse voltage, all right, reverse voltage is applied. Observe the polarity is there. Okay. So we know that diode will not conduct. When diode doesn't conduct, we know that it acts as an open switch, as shown in the circuit here. So there is no current flowing through this particular path, right? Because there is a break in the circuit there. Circuit is not complete. So typically, we have understood now, an ideal diode would have 0 forward resistance, that is RF, we can refer it as RF, 0 forward resistance, 0, sorry, here it has become twice, okay. 0 forward voltage drop. Forward voltage drop means this is the voltage drop across the diode when it is conducting. So that would be 0, Vf would be 0, and infinitely high reverse resistance. Okay, reverse the reverse resistance would be infinite because there is no current flowing through in the ideal diode. Okay, typically these would be the characteristics of an ideal diode. Are you all with me? All right. So this is another circuit where you can just analyze the working of a circuit with the diode there. See, it is connected in parallel here. Okay, this is the DC supply or the source V in resistor, and diode is connected here in parallel. So if the applied voltage V in, if it is less than 0, so we know that the diode will not conduct, so it acts as an open circuit. So the output what you get will be simply V in, what is applied here, isn't it? Right? So if the applied voltage V in is greater than 0, then the diode would be conducting. So this becomes shorted. So the output what you get here will be 0, because the circuit is completed here. Okay, 0 in the sense, of course, there will be some drop here that would be measured here at the V out, but ideally, I'm talking about ideal condition. Assuming that when the diode is conducting, the voltage drop across the diode, assuming to be 0. So if V in is greater than 0, the diode is conducting here, so it becomes a short circuit. So the output voltage what you measure will be approximately equal to 0, right? All right, so now tell me, this is a poll question. Answer this. In which case there is a flow of current? You will be answering in the chat box. There are 3 conditions there, A, B, and C. In which case there is a flow of current from A to C? Okay, your response would be the proof of your attendance. All right. Okay, fine. Yes. Okay. Yeah, all have answered. Yeah, fine. We'll continue. So all agree that in the conditions given here, only in condition A, the figure A, there will be current flowing through A to C, right? So in this second, because diode 2 is connected reverse, there is no completion of the circuit. So there is no current flowing through this. And here again, if you are talking about A to C, diode D1 will be reverse bias, which would not conduct, and the circuit is not complete, right? So I hope you are with me and you agree with me that the current will be flowing in only this condition, A, where both the diodes will be forward biased. Okay, fine. So now we have understood the typical condition. Okay, and there we have assumed, now we have understood that there would be different types of resistance that we can talk about when we are discussing PN junction diode, right? So the 2 types of resistance would be say the forward resistance and reverse resistance. Okay, first let us discuss reverse resistance. Reverse resistance is the resistance offered by PN junction diode when it is reverse biased. obviously, as the name indicates, right? So when the reverse bias voltage is applied to the PN junction diode, what happens? We are already familiar that the width of the depletion region increases, right? Whenever the reverse voltage is applied to the PN junction, the width of the depletion region increases, which would be the barrier to the flow of current, right? So hence there will be large amount of electric current that would be blocked by the depletion region. In other words to say, reverse bias diode offer large resistance in the electric to the electric current, okay, in the circuit. So the resistance offered by the reverse bias PN junction diode is very large, and typically it would be measured in the range of mega ohms. Okay, that is about reverse resistance. Obviously, in a forward bias condition, we saw that there will be forward resistance as well. So forward resistance is the resistance offered by the PN junction when it is forward biased. So in a forward bias PN junction, there will be typically, we can refer to typically two types of resistance there based on the applied voltage again. So the applied voltage can be DC or AC, right? So based on that, the two type of resistance that we can observe in forward bias diodes are, first is static resistance or the DC resistance, and second is dynamic resistance or AC resistance. So what is this static resistance or DC resistance? When forward biased voltage is applied to the diode that is connected to the DC circuit, a DC current flows through the diode, right? So direct current or the electric current is nothing but the flow of charge carriers through the conductor, that is the device or the diode what we are talking about. So in DC circuit, the charge carriers flow steadily in a single direction or forward direction, right? So the resistance offered by the PN junction diode when it is connected to DC circuit is called static resistance. So it is typically the ratio, it is defined as the ratio of the DC voltage applied across the diode to the DC current or the direct current that is flowing through the diode. So you can, in a simple way, represent it as ratio of the DC voltage to DC current. So what are we talking about? We are discussing static resistance. So static resistance or the DC resistance is nothing but the ratio of DC voltage by DC current. That is very simple, as we know that. Okay. What about dynamic resistance or the AC resistance? So dynamic resistance is the resistance offered by the PN junction when the AC voltage is applied. So whenever we have a circuit where there is AC circuit and the applied source is a AC source, okay, then we say that the diode will be having a forward bias voltage, which is a AC voltage that is applied to the diode. So the current flowing through the diode would also be AC or alternating current. Okay. So the typical response when we measure this VI, when we plot this VI characteristic for such circuit, we observe the variation in the plot in this way. Okay. So here the dynamic resistance is defined as the ratio of change in the voltage to change in the current. Okay. In a simple language to say, dynamic resistance is nothing but reciprocal of the slope of the forward characteristic. Now, how do you measure the slope here? Can anyone tell me? How do you represent slope here for this particular curve?
Ma'am, it will be nothing but uh, V at point A minus V at point E by I at point B minus I at point F. That will be
Okay.
slope, right?
Correct, correct. So how do you put it in a right form? Very good, Ashwija. Can I alter your answer saying that the slope would be y2 minus y1 by x2 minus x1. Will that be fine? Is
Yes,
it?
ma'am.
Yeah, right. So the coordinates in the slope in the curve, what we have here is the slope would be y2 minus y1 by x2 minus x1, right? So from there, we can measure the dynamic resistance as given by the equation here, which is nothing but change in the voltage to change in the current. So I hope you're noting down all these points. It's not only theory you have to note down because you may get some numericals out of all these topics that we have discussed. I hope you are with the notebook and you are jotting down all the important key points. Are you? Yes or no?
Yes, ma'am.
Yes, sir.
Melvin? Melville? Yeah? Okay. Okay, fine. Moving on to approximate model. Okay. So in approximate model, we know that the forward voltage drop here, typically what we will do, we will assume the forward voltage drop to be a constant and the reverse current will be ignored here in this particular model, approximate model, also called as simplified model. So here, the forward voltage drop across the diode will be assumed to be a constant and the reverse current will be ignored. Since it is very small, it will be ignored. Okay. So practically, the all the diodes, practical diodes, what we'll be considering in any of the circuits, they can be treated using this model. Okay, simplified model or the approximate model. So what is it? Observe here. The equivalence model using this approximate model, in this case, it consists of a battery and an idle diode. Okay, as you can observe there on the figure. So consider the horizontal line here from 0 to 0.7. Typically, say we are discussing, say, silicon type of diode. Okay, 0 to 0.7, you have a horizontal line. Okay, this horizontal line indicates that current flowing through the diode is 0, isn't it? So till you reach 0.7, current will be 0. So you will be taking, that is indicated here as a horizontal line. So to this model behavior, we put a battery of 0.7 in the equivalent model, which means what? This doesn't mean that the diode has a source voltage. It is acting as a source voltage. No. So when you measure the voltage across an isolated diode, the instrument will show 0 value, right? So the battery simply indicates here that it opposes the flow of current in the forward direction until 0.7. I hope you are getting me. So as the applied voltage across is larger than 0.7, only then the current can flow. That is, that only then the diode will be forward biased, or say it starts conducting, or it is shorted, or it acts as a closed switch. I hope you're with me. So in this approximate model or simplified model, what we will take this typical characteristics. So if it is silicon type of diode, what we are discussing, then we will take diode or replace diode with a constant supply there of 0.7. That is, it is almost like replacing diode with 0.7 volts. Okay. Or if it is a germanium type diode, then we will be replacing the diode with a 0.3 volts of supply there. So what does it mean in the circuit? Wherever you have the particular diode, whether it is silicon or germanium type, all right. So till the applied voltage reaches that value, 0.7 for silicon and 0.3 for germanium, there is no current flowing through the circuit. Only after that, there will be full current flowing through the circuit. Are you with me? Are you able to understand that? Am I
Yes, sir.
understandable? Okay, okay. So that is approximate model. So in all the circuits, we will be using this method where we'll be replacing the diode with the say cut-in voltage or its typical barrier potential. All right. So yeah, this is what I've just explained there. The figure explains the same. In ideal condition, when the voltage is greater than 0, there is maximum current, that is the diode will be acting as a closed switch, and in reverse condition, diode acts as a open switch. Whereas in approximate model, we will be replacing with the voltage source there, okay, which is required to allow the current to flow through. Okay, so that would be zero 0.7 for silicon diode and 0.3 for germanium diode. Okay, germanium type of diode. And obviously in the reverse bias we will be ignoring, because we assume that since the reverse current is very less, we will be ignoring the reverse condition here. Okay, now observe there are three. Yes.
In the previous slide, we replaced the diode by a voltage source
Yes, that is what I said.
of the same voltage value, right?
Yes, because yeah, because that is the minimum voltage required for the diode to conduct, isn't it? Yeah, silicon, it has a 0.7 volts cutting voltage. All right, after 0.7 volt, the diode will be conducting, right? So we will be replacing the diode, or say instead of replacing, you can also say in series you'll be connecting a voltage source of 0.7 volts in this particular model, in approximate model. Okay, for silicon type we will use 0.7 volts, and for germanium we will replace the diode and the circuit with 0.3 volts. So what does it actually indicate? Only after that value there is full current flowing through it, isn't it? We have already discussed till now. That is the minimum, or the cut-in voltage, or the knee voltage, or the barrier potential. Only after that barrier potential the device will be conducting. That is what we have discussed till now, isn't it? Yeah. So that's why. Yeah. Am I able to clear the point to you, Kate?
Yes, ma'am. Thank you.
Okay, fine. All right. There are three circuits here. For the circuit shown, find the value of I. Use the approximate model of the diode. Please go through the circuits A, B, and C. Analyze them with the approximate model, and see whether you'll be able to find the value of I. I hope you are familiar with Kirchhoff voltage law. Can anyone reply?
Yes, ma'am.
Okay, fine. Yes. So you are in a stage to apply KVL here. Yeah, discuss one by one there, circuit. So the first circuit, observe there, circuit A. How do you interpret the circuit? What will be the current I? I want you to analyze.
It will be normal, like normal applying Ohm's law.
No. Observe the circuit first. Ashwija, observe the circuit. 12 volts supply, DC supply is connected to the silicon type of diode there, where a series resistance is connected. A resistor in series is connected. Okay. Observe that circuit. There is some mistake in the circuit. What is the mistake? Will the diode conduct in this circuit first of all?
Is diode reverse biased?
Exactly. Isn't it? The diode is reverse biased. Will the diode conduct? No.
No.
The diode is, yes, the diode is reverse biased. The diode will not conduct. So the circuit is not complete. So there is no current flowing through the circuit. So how can you measure I there? Okay, so the answer would be, how do you represent your answer there? Since the diode is reverse bias, the current I will be 0, isn't it? Okay, now observe figure C, circuit C there. Then we'll come back to B. Observe the circuit C. Will there be a closed loop where the current can flow through the circuit? Again, the negative terminal of the battery is connected to the anode terminal of the diode there, the top diode. So which will be causing, wherein that diode, top diode will be reverse bias, right? So it acts as an open circuit there, top diode. Correct? So the circuit is incomplete. So there is no current flowing through that circuit again. Are you with me? Are you able to follow that?
Yes, ma'am.
Okay. So now coming to B part, circuit B. Circuit B. So there in the second loop, that is in this loop, okay, observe that the current can flow in the direction as shown here according to the arrow there. Okay, now apply KVL. Can you apply KVL and find what would be I? So how do we apply KVL here? Can anyone tell me?
Is it 1 amps?
It is 0.965. First give me the KVL equation there. Going to the final answer is not important. You have to know how to arrive to the final answer.
20 minus 20i.
No, tell me the equation. Come on, first. So how do we go there? If we are going in this direction, say I into R, isn't it? Here, following the mouse there. I into R, yeah, plus the drop across this, let us call it as VD, plus VD. And as I'm entering this negative terminal, so I'll say minus 20 is equal to 0. Does it make sense? KVL. The drop across, the drop in the closed circuit, the summation of drops in the closed circuit will be equal to 0. That is KVL, isn't it? So if I'm going in this direction, I into R plus, sorry, is it right? Okay, let me write. 1 minute, let me write that. Yeah, I into R plus VD, I take it as VD, minus 20 is equal to 0, isn't it? So I'll keep IR to the left hand side. Please, you follow my instructions there and you can write down there. So on the right hand side, it will be 20 minus VD, right? I into R is equal to 20 minus VD. So 20 minus VD, we will take it as the typical value cut-in voltage of the silicon diode as it is indicated. So it will be 0.7, 20 minus 0.7 by R. So I will be equal to 20 minus 0.7 by R is 20. Isn't it? Am I right? I is equal to 20 minus 0.7 by 20. Am I correct there? So are you getting 0.965 amps?
Yes, ma'am.
Yes, ma'am.
Okay. Yeah. So you have to write down all these things, sir. Just listening, it will not help. Okay. Now try to find for the diode circuit shown here, determine ID and V0 using approximate model. That is the first circuit. Second circuit is nothing but the equivalent circuit of the same. This circuit, it is the equivalent circuit of the top one. So this is the main circuit. For the diode circuit shown, determine ID. Determine ID and V naught using,
Excuse me, ma'am.
yes,
Ma'am, in the previous slide, can you please get that previous slide back?
okay.
Ma'am, in the C circuit, ma'am, like we can see that no current or voltage flows through those both the like either of one diode, but in the diode there is no flow of voltage, it's reverse bias, right?
Hmm.
So there is no flow of voltage, but there is a flow of voltage through that 10 ohms resistance, no, ma'am. So it forms a closed loop, right? There is a
Uh,
current, right?
where is the flow? What did you say? Come again?
Ma'am, we can see that there is no flow of voltage through those two diodes, right?
Mm-hmm.
So, but there is a flow of voltage through the 10 ohms resistance, no, ma'am.
Ah, yes, yes, yes. Yeah,
So
yeah,
there
yeah.
must be current, right, flowing through
Correct,
it.
correct, correct. Exactly. Very good. Yeah, inside the the loop or the branch there, inside where we have two diodes, that part will be incomplete. But obviously there will be current around the circuit. Correct. Very good. Thank you for bringing to my notice. Yeah, can you tell me what is the current there? Exactly.
What I guess,
So it is 10 by 10 there.
yeah, well,
Yeah, yeah, minus 1. Since the potential, the applied voltage is reversed there, so it will be minus 10 by 10. So
yes,
it will
ma'am.
be minus 1 amps. Very good. Thank you. Who is this? Who is this?
Aveen, ma'am, Aveen.
Again, yeah, yeah, yeah.
Yeah.
Good observation. Yeah. Okay. Shall we move forward? Yeah. Please note that. And yeah, I missed that point. Okay. Okay, for the circuit, I mean the diode circuit, determine ID and V naught using the approximate model of the diode. So can you tell me, apply KVL to this loop and tell me what would be ID? Please solve that. Apply KVL there. So you can go in a particular this direction as the arrow is indicated there. So I want you to try. I hope you know the KVL, how to apply KVL. So if you're going in this direction, following the arrow there. So plus 5 minus 0.7 plus ID into 2.2K is equal to 0. Am I right? Am I right? Going in this direction? Plus 5 minus 0.7 ID plus ID into R here will be equal to 0. So from that equation, you can find ID. Are you getting 1.95 milliamps? Please do it. Please do it. Without doing, you will not get. All right, the solution is here. You can refer, cross-check. ID is equal to, from the equation what I just mentioned, you can rearrange the things and you will get on the right-hand side 5 minus 0.7 by 2.2 kilo. Yeah. So that will give us 1.95 milliamps. And the output voltage will be nothing but I into R. So ID you have calculated, substitute ID there. It will be 4.3 volts. Are you all with me? Hello? Yeah, all these are example problems. You might expect all such circuits there. Yeah. So moving on to piecewise linear model. So this piecewise linear model, as the name indicates, is a model in which the characteristics of the diode is approximated by piecewise linear or the line segments. All right. Now consider that the straight line in the piecewise linear characteristics. So this straight line indicates constant slope, right? So if there is any deviation, if there is any, say, the values are slightly varying, it is not linear, then you will have some slope in the circuit, in the plot, isn't it? So the slope in the VI graph indicates the resistance. So as I mentioned earlier, the dynamic resistance, from there we can find the dynamic resistance value from the slope, from the VI characteristics. So that dynamic resistance can be added in the circuit as indicated here. Okay, so we add a resistor in the diode model. So from the previous discussion, the ideal diode, its equivalent source, all right, and along with the dynamic resistance. So if all are indicated in the circuit, that becomes the equivalent model, piecewise linear equivalent model. Okay, now observe here. We can see from the graph that the diode current changes from 0 to 15 milliamps for the voltage change from 0.7 to 0.8. Are you able to note that? So the average value of the resistance, can anyone tell me here? How do you measure the resistance here now? How do you measure resistance here? Now, the current is varying from 0 to 15 milliamps, all right, for the voltage change from 0.7 to 0.8.
Ma'am, is the resistance 6.67?
Exactly, exactly. How do you take that? The change in the voltage by change in the current, right? So it is 0.8 minus 0.7 by 15 milliamps minus 0 milliamps. So that would be the ratio which will give us 6.67 ohms. I hope you are able to get that. So that dynamic resistance from the forward characteristics will be indicated in the circuit. So that becomes our say piecewise linear model. Okay. All right. Can anyone tell me what is the okay for the network shown? Yeah, all these circuits have directly taken from the prescribed textbook, which is from Nagrad and Gopal. So that's why you can see the figure numbers and all there. Now, for the network shown, determine VO1 and VO2. Can anyone try? What would be VO1? That is voltage at point V01. At this point. Can you just analyze and think and tell me? See, the applied voltage is 12 and the diode indicated here is silicon type. So the drop across this point, how do you measure? It will be 12 minus silicon type means it is 0.7, right? 12 minus 0.7 will be the voltage what you can expect here at the point V01 or VO1. Are you with me? So that would be 11.3 volts. Okay. Now here V02. Can anyone guess what would be V02? If at all, say the circuit is complete and both the diodes are conducting. So if this germanium type of diode is conducting, so what would be this value?
Ma'am, is that 0.82?
0.82.
82.
No. See, to make this germanium diode conduct, how much voltage is required?
0.3 rate.
Exactly. That is the cut-in voltage of this germanium type of diode, isn't it? So to make this diode conduct, the voltage applied 0.3 is enough. So that would be completing the circuit. The diode is conducting. I hope you are able to get that. Yeah.
Ma'am, can
What
you
I'm
repeat
trying,
that?
yes, what I'm trying to say here is, if this circuit has to be complete, if the germanium diode used here, if it has to conduct, then the voltage applied here, V02, 0.3 is sufficient. That is what I'm trying to say. 0.3 volts is sufficient to turn on this diode here, germanium type of diode. It's not that it cannot be more, but what I'm trying to say here is germanium diode to make it conduct, okay, the voltage applied here 0.3 is sufficient is what I'm saying. Okay, so this voltage V02 can be 0.3 if at all germanium diode is conducting. So to make you clear, okay, observe this circuit. Slightly I'm crossing the time here. Okay, now tell me which um, diode would conduct. And obviously, both the diodes will not be conducting there because both are connected in parallel. Any one should conduct. Can anyone analyze and tell me which diode would be conducting? Now, the applied voltage here is 12 volts. Okay, 12 volts. There are two diodes, silicon type and germanium type. And there is a load of, say, 1 kilo ohms, the resistor connected at the output side. Now, the applied voltage is 12 volts. The cut-in voltage of the germanium is 0.3 volts. The cut-in voltage of silicon type diode is 0.7. When the applied voltage is 12, which diode will first conduct or turn on? Germanium, isn't it? 0.3 is enough to turn on this diode. 0.3 volts is enough to turn on this diode. So the circuit path will be this. There will be no chance for the silicon diode to get turned on at all or to conduct at all because the circuit path will be here through via the germanium type of diode because its cut-in voltage is 0.3 volts. Okay, so just as the applied voltage crosses 0.3 volts, this diode starts conducting. So the circuit path would be this. Are you with me? Are you able to follow that point? Are you able to follow that point?
Yes,
Yes,
ma'am.
ma'am.
Yeah, okay, fine. All right, we'll stop here. Maybe we'll conduct and discuss more circuits in the coming classes. I'll stop the recording.